How's everyone doing today? I'm Michael Littlecrow, and this is my learning lab. This is an activity that I designed out of just looking up what the word trigonometry means. It means to measure triangles. So shouldn't we learn trigonometry by actually measuring triangles? I'm hoping you'll find this activity helpful in understanding the connection between right triangles and the unit circle, angles and measurements, sine, cosine, tangent, all of these things from a physical perspective, okay, that hits the cognitive perspective at the same time. So let's go ahead and start over with the activity. Yeah, it's a little nicer. Step outside and have some lush tropical koi pond. Okay, so you should print out, if you haven't already, the from the PDF, the triangle sheet with the 1 decimeter measuring, and this is the technology behind it is we're going to use the metric system, which will help us understand very clearly about what's going on. So we're going to measure all these. Now, if you want to do the first activity, I'm just going to focus on 2 special triangles, the 45, 45, 90. These are the corners are all 90s. They're not marked. If you want to, you can. And then there's the 30, 60. So these are the 2 we're going to use at the start. But once you see how those work, you can do the same things with these other angles, and you'll see how you can really build an understanding about things that are going to come up later and be taught later as well, reference angles, what all that stuff is. We'll do it, we'll learn by doing. Okay, so print this off. Now I've printed it off on a colored cardstock, so it's a little easier. So when I cut them out, they're more durable. Okay, so that's the way. You'll want the data sheet. Now it doesn't have to be, if I've highlighted the 3 angles from the 2 special triangles that we'll be working with. In addition, we've got 0 degrees, which we're going to talk about. There's no triangle that has 0 degrees in it, and there's no right triangle that has another 90-degree angle, because it just can't happen. But those are kind of the extremes, and those will tie us back to this unit circle, which we will be building on next. The first thing, though, is to do a little bit of measuring. Okay, why is this called a unit circle? It's called a unit circle because it is 1 unit in radius. What is our unit? We are going to be using the decimeter. A decimeter could also be thought of as 10 centimeters or 1/10 of a meter, but it is 1 decimeter. That's what makes it a unit. So that's the unit we're going to use, and you're going to see it really empowers everything. And just to this sort of just occurred in a dream to me. Why don't we use a decimeter? It would be perfect. It would fit on a sheet of paper, and it would give us all the decimal readings we need. So this was sort of the insight part. Not that, maybe somebody else has done this, but it just kind of said, why don't we do this? So you can see that the radius is 1 decimeter. Now, with the other part of this I want you to understand is when we measure, there's error. There's a little bit what I call slop, We physically can only get so accurate. So we're going to tie that with some of the theory as well to get very accurate measurements of what we know, realizing that our printers may have printed things slightly different, so and sort of things. And even then, even with perfect things, our eyesight may not be as good in our measuring. So that's what we're going to do. But you'll see all the way around here is 1 decimeter. Now, one of the first things I think I'll do is tie you in with where does the number pi come from? And with the measuring, we can do that. Now, we're going to measure triangles, right? But here he is switching over, measuring circles. Remember, you can also turn up the speed on this and get through it a little bit faster. So what I'm going to do is I'm going to measure the distance around the top half, the hemisphere of the circle, because I'm only using a radius of 1. And what you'll see if I do this accurately, now I'm measuring a circular item with a straight item, and so there's going to be, again, like I said, a little bit of slop. I call it slop. That's my technical word for the day. A little bit of slop in the measure, but we'll see as I measure here, come around, and I should go the other way, but you'll see halfway around here is going to be a number that you've probably seen before. So I'll make a little mark there. And again, I encourage you to do this, to follow along. And I show for, for those who maybe don't have a printer and stuff, you want to just watch. I understand that happens, but the real power in this activity is if you actually do it yourself, or there's power in watching somebody else do it, but it's sometimes, and again, we all learn differently. I'm kind of a hands-on sort of guy. As I told my engineering class, I like to take things apart. That's the part I like, putting them back together. Not so much. Okay, so we've got 2 so far. Can anyone guess what we're going to end up at? Because I want to be able to tie this back to the angles we're using. We're going to start off with using degree measure, which comes from the Babylonian, the Assyrian Empire. That's what they used. Radian measures came along later. And that was probably the part of the history I wasn't too interested in. Now, let's see. It should be, that's 3.1. And you see a little bit, it should be 3.14. And it's a little bit more. It's maybe more like 0.146, but that's my slop in there. So I'm going to do it. We're going to call this side 0. We go all the way around, and this is, we're going to see, we'll call it 3.14. That's what it should have been. I know what it is. It's also called pi. Okay, so halfway around the circle is 3 radiuses, or radii, and 0.14, a little bit more. So that's where that comes from. Now, usually you've seen it demonstrated as the diameter to the whole circle, but I want you to see that since we're using the radius, that's why halfway around here is pi. All the way around the circle would be another pi. So if we end up back here, this would be 2 pi. Okay, and again, you're going to learn more detail from the textbooks about pi and those kind of things, but I wanted you to just see where it comes from the physical aspect of measuring. Okay, now we've got our 45, this is one special triangle, 45, 45, 90. Okay, and let me just put my little square in the corner there to indicate it is a right angle. You can measure it if you like. First of all, I'm going to measure what we call the hypotenuse, the long side. And amazingly, it's exactly 1 decimeter. That was the design. These are designed to fit inside this unit circle, with the hypotenuse being the radius. Ooh, it's going to be so sweet. Okay, so we come along here and we measure. And again, oops, I gotta start at 0 when you measure, right? So there's all these things you forget about having to do because we're so used to having all the measurements given to us. But when you measure here, what we get is 0.71, and it's not quite on the 1, so it's not 0.71, it's a little bit less. It actually ends up being, because again, we know these things, we can look them up, it's 0.707. If you were to round it, it would be 0.71, right? But I want to have at least 3 decimals of accuracy, and actually that's not even exactly accurate, but it's to 3 decimal places it is. What I want you to see is the other side, because it's what's called an isosceles triangle, because a 45 and a 45, they're going to be the same measure. But again, it's always good to confirm by doing, and if we get everything lined up, it's right about there at 0.7, just a little bit shy of 1. Okay, so I'm going to put that here, 0.707. And you're going to see this is going to connect to our unit circle sines and cosines, x and y's. What I'm going to do is I'm going to flip this over, because as we go around, we're going to need to use the back side. So I also want to put 45 here and here. and then my measurements, 0.707 and 0.707. You could put the 1 over here, 1.0, because we did measure that. That's our hypotenuse. Okay, and we'll be using and building this table. We'll be building our own unit circle. And so then that way when you look at the textbook, you'll know where all that came from. You'll just see it all plop. Oh, there's all this stuff there. How did it get there? Well, we'll build it step by step. Okay, so this is a very important special triangle. Now, we got another special triangle. And you'll see why they're special. They're the numbers, well, you think about building. We use these angles probably a lot in building. But again, we're going to just verify that the hypotenuse is indeed 1 decimeter. That makes it the radius of the unit circle we're using. It fits in perfectly. We're going to measure the side with the 30. So again, I start at 0. Let's see, how do I do this? And I hope I'm not making anyone dizzy, but I just want to demonstrate how to do it. And also kind of get us, so it's 0.8, and there's a 6, and it's a little bit more than the 6. I'm not quite sure how much. Actually, I am sure, because it's supposed to be 0.866. So I'm going to put that down as 0.866. And again, the only reason I could get that much accuracy is somebody else with very accurate measurements did this, and with a theory, they matched it from both sides, so that's good. Now this is my favorite one, the side opposite the 30 or adjacent to the 60. So we'll start using that language. So this is adjacent to the 60 degree, but it's opposite the 30 degree. Okay, and so when we measure this, well, that looks like it might be exactly 0.5, and it is. It's exactly 1/2. And the trig you'll find out. So we'll just put that as 0.500 to show the accuracy that's there. Okay, again, we're gonna, and we put our 1 here because we did that. Okay, we'll flip it over. Let's see, the 60's at the top, so we just want to relabel these. I was going to do a double-sided so you could print back and forth, but that would probably be hard to get everything to line up. Well, not probably, it is, and I didn't even want to think about that. So sorry to make you have to do some transferring, but this will all work out very lovely by the time we're done. Okay, and then we'll put our little right angle marker thing showing that that is a right angle indeed. Okay, now we're almost there. We're going to connect this unit circle, which is the starting of, well, I guess triangles themselves are the start of trigonometry. So before we go too far, let's go ahead and come to this sheet, and let's take our 45-degree angle because we've done our measuring. We're going to come back and talk about radian measure. We just sort of, we're set up for that. So what we want to put here is our measurements. So the adjacent side, as we talk of the 45-degree angle. Now this one, we could use really either one, but the adjacent to this 45-degree angle here would be 0.707. Okay, so we can put that there, adjacent, 0.707. And of course, the opposite of this 45 is also 0.70. That's hard. No, don't. And then the hypotenuse is 1. And you could put as many zeros as you like. Now, the start of trigonometry comes from these triangles. They just define something, they call it the cosine. They probably started with the sine, and the cosine goes along with it, but we're going to start with the cosine. It's just the ratio of the angle, the measurements of the sides according to that angle. Angels and angles. Be careful how you spell it too. You switch one letter, now you have an angel instead of an angle. Okay, adjacent divided by the hypotenuse. And now you'll see the beauty. Since every hypotenuse is 1, we're dividing by 1. Well, that's cool because we get back to what we want. So the adjacent side is 0.707 divided by 1. So the cosine's actually going to be 0.707. And if you plug into your calculator cosine of 45 degrees, this is what you're going to get, 0.707. Okay, sine is going to be the opposite over the hypotenuse. And again, since it's 1, it's going to be this measure right here. Now this one's hard to tell which is which because they're all the same, right? And now we'll talk about the exact cosines in a little bit. I want to finish up the measuring part, because to get the exact measures, we come back to a more of a theory, and we do some analytics on it. I'm not going to do it because this activity is about measuring and physicality, but you'll see that in the book, and we'll list it. But I want to show it in a pattern that arrives. So before we can get there, though, we need our friend here. And again, we've already got the measurements here. So we're looking at the 30-degree angle. We've got our radian. We'll deal with that, yeah. The adjacent measures. So the measure of the adjacent side. So 30 degrees is here. The adjacent is 0.866. 0.866. We measured that. The opposite side, so here's our 30 degrees. The opposite side is 0.5. And you could leave it at that, or you could put the other zeros just to show it's very accurate. And the hypotenuse we measured as 1. Very nice. The same triangle helps us fill in this table for the 60, but watch how we have to do this. The adjacent measure for the 60 degree, the adjacent side is 0.5. So it's this side here. 0.500 is physically adjacent. The opposite side, the side opposite the 60-degree angle, is the 0.866. Okay. And the hypotenuse is still 1. And so that allows us to come back and do these. You just kind of see we're actually measuring the cosine and the sine. This is cool. I thought it was cool. I'm excited. Anyway, so the cosine is the adjacent over the hypotenuse, so that's adjacent over 1. So that's 0.866. The sine is going to be the opposite over the hypotenuse. The opposite's 0.500. And we'll talk about the exacts in just a moment as we have our full pattern here. And then, of course, for the 60 degree, we do the same thing, but we get different results. So the cosine is the adjacent, which is 0.500. Now remember, we have to divide that by the hypotenuse, because you'll get problems where the hypotenuse is not 1. You'll get the same cosine as long as you measure everything and you use the correct. We're just being able to do this real easily because our hypotenuses are 1. And that's the way this activity was designed. Okay, and so opposite over hypotenuse, opposite over hypotenuse, boom, we're done. Now, here's a pattern I spotted. I always had a difficult time memorizing the exact cosine and sine measures, and we use them a lot, especially at the beginning, and then so you got to go look them up. Well, we're going to see, like, if you think of half a circle, the 45 cuts it in half. What I want you to just kind of remember, and again, they go through and develop this, each of these measurements come from, are all divided by 2. Why? They just are. Again, my goal here is not to do a lesson on how to come up with these exact measures, but to give you the exact measures and see if you plug it into a calculator, you'll get the exact same decimal that we measured. And we're going to use primarily the measurement ones, but we will refer back to these because oftentimes we need those. Okay, so the first thing is to think everything's over 2. Okay, and now watch the pattern here. For cosine, cosine starts large, gets smaller and smaller. And so the way this works is the smallest one is down here. So I want you to think this is going to be square root of 1, which is just 1. You don't have to have that square root, but I'm going to put it there because that helps me remember. Square root of 2, square root of 3. when you put these in a pattern, you'll see that this is 1/2, this is square root of 2 over 2, this is square root of 3 over 2. Okay, now you'll see the sign goes in a different pattern. It goes from smaller to larger, and so for the sign, the same pattern occurs. We get square root of 1, which again is 1. You'll just see it as 1/2, but this is the way I can remember. Square root of 2, you have to have square root of 2, and square root of 3. So you now have all your special angles, and if you don't have your unit circle with you, this little trick, it works for me, okay? I hope it works for you. So that's going to help us build our unit circle, okay? We're going to come back and talk about radian measures and so forth, but now we need to come back from these triangles, connect it to the unit circle. And we're just doing it with these three. You still have all these other ones, right? And they will work. It's not that they aren't, that we can't get a cosine for them. It's just that they're not as beautiful pattern as this. And I guess for building, we typically will use like 30, 45, and 60s, 90s, and 0 degrees. So that's where that's at. Okay, so now this is the key part. We often talk in trigonometry about reference angles. So let me start with the 45. So get this guy out of there. Okay, so we've got 0 degrees here, and then the way the Babylonians measured angles is their complete base was 60, and so when they came to circles, they divided it up into 360, which is 6 60s, and that gives us our 360 degrees all the way around. Okay, so we'll start counting here. We can see we can put this triangle into the circle. The hypotenuse here is a radius of 1, so a 45 degree, watch this really cool trick. I don't know if it's a trick or not. People don't like me saying tricks, but I think it's like magic. Math is, the magic part is trying to hold down your triangle while you draw a line. So I want to kind of create my own. So I've got a straight edge here. Let's see if I can, so I'll come out here. So I'm going to just label it my 45 degree angle, and we'll connect it to the radius. And it's, again, we can kind of see when we're it's not necessary exactly, but watch. The x-coordinate of this point on the circle is going to be, the x-coordinate is 0.707. The y-coordinate is 0.707. So what we're doing with trigonometry is, here's the x-coordinate of this point, and the y-coordinate, I'm going off the paper here a little bit, 0.707. Okay. And you'll see that that x and y coordinate of that point on the unit circle are also the x, the cosine. The x is the cosine, the y is a sine, because we just did that with the triangle. So this is where the triangles connect with the unit circle. Oftentimes we're talking about things that are circular and stuff in the math that we're solving, so we forget about the triangles and we start coming back to this unit circle. But a lot of times we were taught, well, I was taught without this connection. I made the connection later and everything seemed to make so much more sense. Typically we don't have a lot of time, so the quicker we can make the connections, the better we can understand. Now here's the key part. All I really need to know is what happens in the first quadrant. You'll see I can figure out in each of the other quadrants. But to get into the second quadrant, I have to flip my triangle over, and that's why we wrote on the back side. And again, I've got my other, so this is not 45 degrees, it's 45, 90, plus another 45, that's 135. So that'll be 135 degree angle. Maybe I should just try, let's see if this works. And again, mine might not be as beautiful as yours, but you can get these printed out too. So we can just kind of go like there it is. So that's a 135 degree angle measuring from 0. And come over here. And what is the x-coordinate of that point? Well, it's 0.707. 0.707. Yeah, that's right. But it's negative, right? Because I'm on this side. I've gone in the negative direction from 0, 0. So I'm still in the coordinate system. So I can label this as negative 0.707. That's the x-coordinate. And remember, it's actually going to be the cosine of 135 degrees, because you'll see the sines and cosines, they change the signs from positive to negative based upon which one we're talking about. Now notice the y-coordinate is also 0.707, but it's a positive because we're up in the positive y area. Okay, so we're building our unit circle, and again, a lot of times you'll see them, and we could replace this with our special angles, right? Or exact, right? It's negative square root of 2 over 2, and this would be positive square root of 2 over 2. Okay, so we can label it any way we want, but now I hope you're making those connections between the triangle, the circle, sine, cosine, x, y. Okay, and again, we can flip it down here. The thing we have to make sure is our hypotenuse is always going to be the radius from the circle. So, you know, you can't measure, I mean, it looks like you could, but this is meaningless here. Well, I guess it's a radius, but it's not really helpful. So we always measure from the center of the circle, so that's where one point goes. And so again, this is going to be, so this would be another 45, so that's 180 plus 45 is going to be, what, 225 out here. And again, you may want to speed this up as you need or slow it down, but or turn it off and just do it all on your own once you catch the pattern, and then go to the end. And so this is our 225 degrees, and again, right here, our x, we're in the negative direction. Our x is going to be negative 0.707. Kind of blocking off there, right? We'll move it up. And our y-coordinate this time, we're down in the negative y territory, is going to be negative 0.707. And again, we could use our exact angle, or exact measurements, or exact numbers. They are exactly equal. Put this in your calculator, square root of 2 divided by 2. You will get this decimal. Okay, so we start building that, and now we've got a way. It's, you know, memory is great, but when it fades, it's better to have a way to recreate those things we might have forgotten. Okay, and again, we've got one more over here. Again, this is not a very, because it's always based off of the x-axis, so we don't use it. I mean, we could, but it's not the right way to do it. We always want the 90 degree, we want to measure off the x-axis. I mean, sometimes it works, but sometimes it doesn't. So here's our radius of 1. And again, this is going to give us it's 225 plus another 45. So this is 270. Down here, we have a 45 added onto that. That's going to be 315 degrees. And again, we get back up to here, 2 pi or 360. Okay. So there we are. And again, our this time cosine is positive because we went in the positive x direction. That's why we want it that way, 0.707. And the sine is going to be negative 0.707. Okay, and again, we can use our special angles, or our exact measurements, or, well, not measurements, exact mathematical numbers, because these will carry it out to many, many, many decimal places. I think like an infinite number. Okay, transcendental numbers, something like that. Okay, so that's one way we do. Okay, so let's connect this with radians. Okay, and then we'll throw in the other one, and then we'll be sort of done with this activity, and hopefully it makes everything make more sense. So what we do, if this is pi, wouldn't it make sense that up to here, this is half of the circle, so this would be pi over 2, half a pi. So it is. It's 90 degrees, but we also call it, it can be called pi over 2. Now the difference is the way they measure it. 90 degrees is that there's 90 little slices, and that's where it gets us, because out of the 360. The way they measure radians is they actually get a little speedy car and drive along here, just like we were doing. And if we measured it, if you take pi over 2, you'll get half a pi, which I didn't do that earlier, so I don't know what the decimal is, but the decimal is, you'd actually be able to measure it if you measured along this circumference, because that's how we got pi, isn't it? We measured, it is 3.14 decimeters, because the radius is 1 decimeter. Okay, so it's a measurement along the circumference. And then we use these symbols just because they're easier to write than expanding out. The thing is when we're dealing with math that involves an angle, oftentimes we're shooting off into a far distance. And so a little error in the beginning creates a big error 100 miles down the road, with, you know, if you're trying to land on that place. So to get the great, you know, when you go a long distance, you want great accuracy in your measurements. So that's why we do it this way. Well, this is pi over 2, and this 45, it literally does cut it in half. This is going to be pi over 4. And so now what I'm going to do is I'm going to count. I'm going to show you how you can kind of count pi over 4. So these are every 45 is a fourth of the pi. And again, it's the thing that's kind of confusing is it's not a fourth of the circle, it's a fourth of the half of the circle. All right, that's how we're doing things, because we're only using the radius, which is halfway across the circle. Okay, so we got to make that connection. We tend to think of the whole circle all the time, but when we're doing trig, we're really dealing with just half the circle. When we're dealing with the radius, we're dealing with halfway across the circle, and that's where it all connects. Okay, so you see the 4 pi's, 1, 2, 3, 4. Pi over 4. I'm going to call this, because I want to do it by counting, 2 pi over 4. And yes, it does reduce down to pi over 2, but I want to count. So 2 pi, and then what comes after 2? 3. So this 135 is also going to be 3 pi over 4. Pi itself will be 4 pi over 4, which the 4's cancel, and that's just pi, but I want to count, okay, because it makes it easier for me. So after 4 comes 5, so that's where I get this one. This is 5 pi over 4. Sometimes it's better not to reduce fractions, I think. 5 pi over 4, there it is, see. And then 5, what comes after 5? 6. So this is, make sure everything's there. This is going to be 6 pi over 4, which, yes, it does reduce down to what? That's going to be 3 pi over 2. But see, it kind of, I don't know, it blows me off. 6 pi over 4 is better, because then I get to this one, and that's going to be 7 pi over 4. And that doesn't reduce, so we just leave it that way. But if you do this as 3 pi over 2 and then go to 7 pi over 4, I don't make those connections. Maybe I should, but I don't. The symbolically, that doesn't speak to the way I think. I like the degrees, 270, 315, that makes sense to me. And when I leave the radian measures unreduced, then it makes a lot more sense to me. And again, what we get up to here, when we get all the way around, what is this? This is 8 pi. We've counted 8 of them over 4, which reduces down to 2 pi. Sure, we got it. And yeah, I like using 2 pi rather than 8 pi over 4. But to build the understanding, that's where we get. Okay. And again, if you take off, you take off. But the whole idea of this is, once you get started, it gives you something that you can kind of work with, play with, and build a deeper understanding. And that's why if you do this cardstock, you still have them. And when you get a problem down the road, maybe you pull it out and maybe it's helpful. Okay. Here it is. So we've got the 30-degree angle is down a little bit lower than the 45, and we can kind of see that. So let me see if I can just, without the ruler. The ruler was kind of causing more problems than it solved. So this is my 30-degree angle. And again, I've got my x-coordinate of the point and my y-coordinate of the point, which we also verified are, these values are the cosine, the x is the cosine, and the y is the sine from when we were doing our chart. So again, we can put our x and y here. And they're both positive. We can also use our exact values, which is, remember, this was square root of 3 over 2, and this is 1 over 2. So it kind of helps us build us. Remember, x went from larger, or the x coordinates go from larger to smaller because it starts here, gets up to here. I guess we could talk about what is the coordinate down here at 0 degrees now, can't we? Maybe I'm going in circles, but maybe I should be going in circles, right? So this is going to be 1, 0. So we'll get back to our table there, and we'll put all that stuff in there. 1, 0. And what's this going to be? This 90 degree is x is 0, y is 1. So this is going to be 0, 1. Okay, so those are, and once we get this filled in, now watch, to get that 60 degree angles, you'll see we have to kind of flip the triangle because we need that hypotenuse to be the radius of this circle. And this is why we've got these other numbers. And notice the sine and cosines have switched places. Now with the 60 degree, x is 0.5, y is 0.866. And you kind of see it because they come from the same triangle. Now, otherwise, the way you teach it in abstraction, you just see these things as different things. You don't see them as connected. But, on a right triangle, if one angle is 30, the other has to be 60. These are what are called complements. They work together, and they're connected. They're interchangeable. I mean, when you're using one, you've got the other there. So again, we've got our x is 0.5, and our y is 0.866. And again, x is the cosine, y is the sine. And we've got 1/2 and square root of 3 over 2. And again, you could do square root of 1 over 2 as well. I usually don't write it once I remember it, but again, it helped me to see that pattern, that there was actually a pattern there. But if you leave it off, you don't see the pattern. I didn't see the pattern. So we start seeing. And the thing is notice the 45 degrees are like one set of spokes around there, and the 30s and the 60s are another family going around, and so they're counted separately. And yet when we teach you trigonometry, typically, when I was taught trigonometry, they're just thrown at you both at the same time, and you don't make this connection because you don't cut out the triangle, you don't measure it. I'm hoping that this will change that for you so that you can make greater progress, faster progress than I did. So this was a 60 degree, 30 degree. So we can talk about this. So notice, so we kind of have to now erase this 45. How many pi's are we going to get? We're going to get 1, 2, 3. Notice 30 degrees. This is another 30. This is another 30. So we're going to get 1, 2, 3, and then we'll see. Maybe I should keep going. We're going to get 6 pi's. We're going to get 6 slices of pie in the half of the circle. So I don't know. Maybe I'm a little bit ahead of myself, but it just seemed natural that the 30 degree, it's going to be 1/6 of the slice. So it's going to be pi over 6. So what is 60? It's going to be 2 pi's over 6. 2 slices, right? 2 pi over 6, which does reduce down to pi over 3. But now at pi over 3, you don't necessarily see that connection to pi over 6. So I like to at least have it here in its unreduced form. And then what is this? Well, yeah, it's pi over 2, but it's 3 pi over 6. Because we're just counting our ways. How many slices do we have? And after 3 comes 4, so the next one, which I'm getting a little ahead of myself here. See, sometimes you want to put it like, that's not going to work, is it? Nope. So we have to go with this, and now it fits, it goes to the angle there. But when you try to do this with in abstraction, sometimes things that are not physically possible in abstraction seem like maybe they would be. So there's a 30 degrees from 90, but it's now what? This is, let's see, we go 90 plus 30 is 120. So it's 120 degrees. And it's also, again, we've got our x is 0.5, but it's negative because we're in the negative direction. negative 0.500. The y is right here. It's 0.866, and it's positive because it's in the positive right direction. And again, we can use our exact, so 0.5 is a half, so that'd be negative a half, and this would be square root of 3 over 2. You see how you can, as you get going with these, you become connected to them. And what is this going to be? That was 3 pi over 6. This is going to be 4 pi over 6. So 120 is also 4 pi over 6, which does reduce, yes, to 2 pi over 3. But I've just lost the connection, right? Here, I know it's 4 slices over. Okay. And then we've got our 30-degree angle. And we're almost done with the main part of the activity, and then the rest is for you to kind of go on and explore. But I wanted to at least build and show you, these are what we call reference angles. When we talk about a 30-degree reference angle, this, which is going to be 120 plus 30, is going to be a 150. We refer back to the 30-degree angle because that tells us everything we need to know. That's what a reference angle is. Refer back to the angle from the first one. But that has taken me a long time because the way to understand, because the way it's defined, it just never made sense to me. I don't know. I'm dyslexic, and my reading abilities are not always as strong as I'd like them to be. But they also, I get more creativity. Some people say I make things up, but I comprehend what I want to comprehend, and I want a beautiful world, so that's okay. I see beautiful things, be nice to people. 120 plus 30 is going to be 150, so we do that with the measures that way. It's also going to be, so we were at 4 pi over 6, it has to be 5 pi over 6. Sorry, I got to pay attention to what I'm doing, right? 5 pi over 6. And again, we see it from here. The x-coordinate is 0.866, but it's negative, right? Negative 0.866, and the y-coordinate is 0.5. Now, I'm not doing this to make something beautiful that you would keep this necessarily. You might want to do it. We'll put a printed one in there. The key is when you do something physical, it sticks deeper in the brain because your hands are moving. You're engaging more of your brain's physical real estate. You're spreading out the learning throughout the brain. And so then you get all these different things that could trigger the memories that you went through. Now, for negative things, that's what we use that word trigger, but it can also trigger positive things. And that's what we want to do with math, is when we concentrate and work in a physical way, we trigger back what we've learned. And isn't that what we want to do? We spend so much time in math education teaching and teaching again. And I'm not going to blame the teacher. I'm not going to blame the student. It's just, it doesn't always work. Sometimes it does. Some of us remember and go. And that's what we have to do, is the things that work, the things that were skillful, let's do them more often. And what works for us, let's do it in that way. I'm just sharing with you something that worked for me in making these connections. Okay. So where are we? Okay, and again, we can use our square root of 3 over 2 and 1/2. And we keep going around. So this is, that was 5 pi over 6. This is going to be 6 pi over 6, which is also just pi. But again, we see how we count, and we can see you kind of have to erase these pi over 4s, and you just see the families of the pi's over 6. These slices, 1, 2, 3, 4, 5, 6. 30 degrees, 60 degrees. They're brother and sister. They are partners in life. 45 is its own partner. It has two 45-degree angles in there, but that's what happens in the system. Okay, and then and you'll see these other. That's what all these other angles are in there. 40 has a partner in 50, and you're going to see that they switch roles, but they're connected. Everything is connected. Everything is related. And so when you learn in this way, hopefully it will be there. Okay, where do we go from here? Again, you can continue, and it's, you can turn off the video anytime you're ready or done. I'll just keep going because I'm having fun. And maybe it'll be helpful in spotting out something somebody wants to stay on. So we just keep making this. So this is 180 degrees plus another 30 degrees. That's add that on. That's going to be 210 degrees. And my pen is not as active as it was. Let's see if I can. There we go. Good enough. So 210 degrees, and remember that's going to be 7 pi over 6. So that's why I do this, is so I can count 7 pi over 6. And you might even start remembering, oh yeah, 30 degrees, the x is going to be 0.86. Let's see, blocking. Sorry. That's why you kind of have to have your own. Let me put it up here, 0.866. But remember, we're in the negative direction in the x, and now we're in the negative direction in the y. So that's also going to be a negative 0.500. And again, we can use our square root of 3 over 2 and our 1/2 here, just making sure we get our signs right. Okay, and you're going to see that this one activity, I think, will be worth the time, because there's a lot of separate lessons in here. We start talking about reference angles. We start talking about, what else do we talk about? You know, these special triangles. Anyway, a lot of lessons in here, and counting, going between radians and degrees, and you can kind of see there's, you know, 3.14 radians equals pi, which also equals 180. 180 degrees. Okay, so we keep going. Okay, next, 60 degrees. How does that fit? We just flip. Nope, it's not that one. This is where this was helpful for me, because if you do it on, I try to like draw them without having them. It's really hard, but when you have the pieces, they only fit one way, right? From the center, the hypotenuse has to go from the center to the edge, and then you've got your x and your y coordinates right there. The funny thing is I've been teaching trig for over 20 years, and this thing sort of came to me, I think it was about 4 years ago, and this is the first time I've actually made a video of it. I did it in a class once, and it seemed to work pretty good, but anyway, let's see. So that is 210 plus 30 is 240 degrees, which also 7 pi is going to be 8 pi over 6, which, yes, does reduce down to 4 pi over 3. Yeah, 2 goes into both of those. And it's going to have an x-coordinate of 0.500, and it's got to be negative because it's in the negative x direction. The y-coordinate is going to be negative 0.866. Okay, and again, we can use our negative 1/2, negative square root of 3 over 2. Okay, and we just keep going, and let's go ahead. So that was 8 pi over 6. This is going to be 9 pi over 6, which, yes, does reduce down to, what's that? 3 goes in about 3 pi over 2, which is over here. Yeah, it works both ways. But when I'm counting with the pi's over the 6, it's a 9 pi over 6. And again, it's going to have, I guess I didn't do the coordinates, but it's going to have an x-coordinate of 0 and a y-coordinate of negative 1, because we're down here. I guess we should come back up to, well, we did the 90. We just never did pi. We left pi out. So pi is negative 1, 0. So x is negative 1, y is 0. And let's go back. Yeah, 0 we did. Okay, we got everything now, except for these last ones. I'll leave that for you to keep going through. So this is going to be here. This was 9 pi over 6, so this is 10 pi over 6, which, yes, does reduce down to 5 pi over 3. But you start to see how they're connected. And then we go, another one is going to be over here, and this is going to be 11 pi over 6, which doesn't reduce. And then 2 pi is 12 pi over 6. So we got all the way around, and we can fill these guys in, and our x's and y's, and which gives us our sines and our cosines. And that's how we can create the unit circle from scratch if we needed to, with just a little bit of remembering. Okay, so we come back to this table. What are the important ones to get at least get us started? We've got them here, and what we've added in here is the radian measure. So this is pi over 6. 45 is pi over 4, and 60 we could I'm going to do it as both. It's 2 pi over 6. I want you to make that connection, and it's also pi over 3. In the textbooks you'll usually see pi over 3, but I want you to remember it's connected back to the 30-degree angle. It's connected back to this pi over 6. It's 2 of them. So that's good there. Here 0 is also 0 radians because there's nothing to measure. We can't measure the triangle, so we can just kind of skip through there. But the cosines are actually exact. The approximates are going to be the same. So right, what is the cosine going to be? It's going to be 1. That's the x-coordinate. The sine is going to be 0. Okay, so 1 and 0. You can't have a triangle with a side of 0, right? And then the 90-degree, that is pi over 2. Or again, you could think of it as 2 pi over 4 or 3 pi over 6. Let me just kind of put that note there. 2 pi over 4, which is also 3 pi over 6. Okay, so it gets counted 3 times there. And what we get is that, again, we don't get a triangle, but we do get, in this case, x is 0, y is 1. X is 0, y is 1. Cosine 0, sine is 1. So those are our kind of main guys. And then these other ones are there. If you'd like to kind of keep practicing on your own, you can see that those angles are there too. You can use your calculator to get it to 3 decimal places. The measuring gets you pretty close to 2 decimal places, but even to 2, it's not really accurate. Gets you at least to 1/10 of 1 decimal place, which isn't going to work for what we need. But connect the theory with the physical part of it. So that was my beginning activity. So if you can fill this in, fill in your own unit circle. Again, the action that you're taking of physically doing it is bringing it deeper into your mind. Maybe try it again all on your own, because then you don't have my voice. But maybe that was helpful because you're hearing my voice. It's connecting. But sometimes the brain works better when we're listening to our own thoughts. So again, I hope you found this activity helpful. Let me know any insights you got, anything that you think might be better. We can build on this and keep it moving forward. So I guess it's time now to go back inside and get some other stuff studied. So we'll get working on that, but that hopefully will help connect everything else that you're going to learn, at least in the first few stages of trigonometry. Hopefully it makes those connections stronger, sooner, so that the learning occurs more deeply and in a way that sticks. Take care. Be well.